Climbing gears are used by rock and ice climbers, mountaineers, and alpine skiers. Safety is number one. Lightweight and strength comes next. The tolerance should be extremely low, as failure in these parts are not acceptable. SolidWorks applications are used to fabricate the 3D designs electronically and use Abacus CAE to use structural analysis. Changes in designs were made in order to make corrections and have improvements.
The most basic tool in climbing gear is the carabiner, because it is the link between different pieces of equipment. For the design, I started off by looking at existing designs such as this one and this one. I came up with the idea to concentrate the load along the closed side of the carabiner, as that side is the strongest one. I did this by giving the carabiner an irregular triangular shape. The clip prevents the carabiner from rotating upside down or becoming subject to cross-loading, which is loading along the horizontal axis. Shown dimensions are in millimeters. The opening of the carabiner is as big as possible for easy hooking and unhooking of ropes. Most of the load will be carried by the inside part of the cross-section. That is why more material was added there. Stress analysis on the carabiner with that cross-section shows stress concentrations at the top and bottom of the inside of the load-carrying axis of the carabiner and low stresses on the outside. So in order to make the design as efficient as possible, the cross-section was altered. This results in lower peak stresses on the inside surface of the carabiner and lower stresses on the outside surface of the carabiner. The final product has an aluminum core and opening link and a steel clip. The stress analysis shows that the carabiner can safely carry a load of 14 kilonewtons and weighs 17.65 grams.
I took apart Gymline. This is how does Gymline look like and how people write the Gymline. I did CAD up and my initial thickness was 0.9 millimeter and I picked aluminum alloy. And I set boundary condition on the wheel to the fixed Gymline. I set the load at the bottom hole as 1000 Newton to make worst case. This is result of Abacus simulations of stress and deformations. For improvements of design, I changed the thickness to 1.3 millimeter and I add additional hole at the backside to connect with carabiner for user safe. And I set same material as a aluminum alloy and same boundary conditions and load, and this is result of Abacus simulations. And I can check magnitude and deformation are less than before. It is how to connect carabiner with Gymline. If Gymline is derailed by some reasons, it could prevent the user from falling down.
Crampons are designed to security travel on snow and ice for mountaineers. What I focused most on my design was three features: lightweight, adjustable for multiple sizes, and strong enough to support the shocks of ice and rocks, and especially the spikes. For my analysis, I added the boundary conditions on the top surface of the crampons, and I added my force concentrated on each spike. When running the analysis, so I realized that the front end spikes are the most fragile. So I added some reinforcement to it, and this has decreased a lot the stress concentration on this part. My final design, I chose the material as aluminum as it is an ideal lightweight for alpine climbing. Each crampon weighs 65.4 grams.
We are focusing a new climbing gear product, CAMs, and this is an assembly drawing. For this product, we only focus on the top part of the CAMs. This is the first design. It has a bigger hose. The material is aluminum. Here is a boundary and loading condition. Here is an Abacus simulation. As we can see, the stress concentration was around the hose and the edge. And this is the result of the displacement. In order to reduce the stress concentration, Smaller holes are needed. This is my second design. I increased the thickness by 1 inch. And here is the boundary and loading condition for the second design. Here comes to the result for the second simulation. The stress concentration as well as the displacement were reduced significantly.
The ice climbing axe is an essential tool keeping you stable up the mountain. Pick, carabiner hole, adze, shaft, spike are key components. We are going to inspect the strength and the weight of this tool. By using the axe in a cane-like manner, holding from the head, we can get this kind of stress contour in the stainless steel material we selected. The forces and the stress concentration differ when the axe is used to slash, grab into the snow or ice. Another form of the axe was examined from an existing design. This one has a reverse negative pick end and has a curved shaft. This dimension is more efficient in swings and is easier to remove from the ice. However, it loses leverage and security when the mountain is steep compared to the first model. And here are the stress contour and the deformation. This is the revised model, which is the combination and the optimization after observing the previous analysis. The pick is remained classic with a positive curvature, and the shaft is slightly curved, so the axe doesn't lose the ability to anchor the surface, while having a better technical mountaining efficiency. I took away a good portion of a cross-sectional area since there weren't any danger. It would be nicer to lose as much weight as possible. It can be coated with other lighter materials around the shaft 2 to 3 centimeters thick with ceramics, rubber, or aluminum. The image shown is just the steel material without the coating, which only weighs approximately 1.3 pounds. You can now see that the stress concentration are greater in the shaft area as it is thinner. However, the coating will support that part. The larger cross-sectional area proved to show less stress. Also, the loading is exaggerated here as the axe is supporting 500-pound individual and is in multiple directions.